Thank you, everybody, and thank you, Camila, for the introduction. Hi, everyone. I'm Visar Berisha. I'm a professor at Arizona State University. And in my lab, we study the human voice, and in many different contexts, typically using computational tools and machine learning, artificial intelligence. So in the past, we've done work on using speech, voice, as a biomarker of human health. And more recently, I've really been interested in how can we develop tools to mitigate risks from voice cloning and really to, I think, sort of prepare for this future that's coming. I think in the not too distant version of the future, we'll have many voice-based AI agents that we'll be interacting with. And generally speaking, it'll be important to know whether the person on the other side is a human or an AI. And so that's the purpose of the talk today, and that's really what I'll be discussing. Some work that we've done in this area. Before I do that, just as a very quick primer on generative technology, by virtue of all of us using the internet and producing different types of media voices, now companies have made use of these large sources of data to develop generative models, generative speech models, and those can then be used using very short clips of our voices to effectively generate synthetic replicas of our voices. So with less than 5 minutes of speech from someone and a 5-minute or a $5 11 Labs subscription, you can generate a cloned version of their voice and make it say whatever you'd like, right? And these models are really, really good. So what I'm gonna do here is I'm gonna play 3 short sentences. You'll recognize these as being from my voice. And then we'll go ahead and have a quiz afterwards. You guys will tell me which one is AI generated. One of the 3 never came out of my lips, okay? She had your dark suit in greasy wash water all year. Brush fires are common in the dry underbrush of Nevada. Don't ask me to carry an oily rag like that. Okay, so whoever thinks A is the fake one, raise your hand. Okay. Whoever thinks B is the fake one, raise your hand. Whoever thinks C is the fake one, raise your hand. And who doesn't know? Okay. Yeah. So this is amazing, right? So it's split 3 ways. So basically a third picked A, a third picked B, and a third picked C. The fact of the matter is B is the fake one. And so whoever picked B, you have golden ears, congratulations. But the rest of you shouldn't feel too bad. Actually, we're only able to detect synthetic voices now with about 50% accuracy, and as the professor here reminds us, just random guessing is 50%. So 60%, just a little bit over random guessing. So people have said, well, then maybe we can turn to AI. AI helped generate the technology to develop these voices. So maybe we can use AI to detect AI. And is that a viable solution? Every year, or actually periodically, it's not every year, there's this challenge that is run. It's called the ASV Spoof Challenge. The idea is they release real and spoofed voices, and it's up to the community to develop algorithms to tell real versus fake voices. There's many different sub-challenges. Each one of these lines represent the sub-challenges of the ASV Spoof Challenge. The x-axis is the last 3 times it's been run, and the y-axis is the accuracy of these AI algorithms for detecting real versus fake. The actual numbers don't matter. What matters is the slopes. So as you can see that they're all trending downwards. And the reason is that as you have improvements in generative AI, the ability of AI to tell what's real and what's fake declines. And moreover, even if you have a really good model, the moment you introduce a really good model to detect real from fake, the moment that you introduce a new generative model, a new model that generates voices, the detector fails. So there's this constant cat and mouse game. So declining performance, cat and mouse game. This is one of the reasons why I think using AI to detect AI is not a feasible approach moving forward. And again, random guessing here is at 50%. So even in 2024, many of these methods are just above random guessing. This is really problematic because lots of bad guys have started using these models for nefarious purposes. So during the last election, we had a group develop a synthetic version of Joe Biden's voice, encouraging people not to vote. In Arizona, a mother was extorted for $1 million. Thankfully, she figured out that it was fake, but the extortion scheme went by, they took samples of voice from her daughter's social media page, generated a synthetic replica, and made her believe that she was kidnapped, and asking for $1 million. And then in the entertainment space, so this is George Carlin, he passed away many years ago. However, some individuals took generated a replica of his voice and his family, then sued them because that was a real intrusion of privacy. So this is becoming, I think, a problem, and it'll continue to become more of a problem moving forward. And if we can't use AI to detect AI, what sort of other approaches exist that we can exploit in order to mitigate the risks associated with this approach? So as I mentioned, in my lab, we study the human voice in many different contexts. And it's useful to step back just for a second and to think about how unique the human speech production mechanism is. So, and we can sort of do this together. Think about when you speak, what's the first thing you do? The first thing you do is you take a breath. And then as you exhale, air from the lungs comes and excites your vocal folds, sets them into motion. So this is your vocal folds opening and closing. If you put your hands right here and say, ah, you can feel them. Go ahead. Yeah. So this gives you your unique voice. This is why my voice sounds different from your voice, and your voice sounds different from her voice. And then we can shape this voice into different sounds, ah, e, u, a, s, t, g, by moving our articulators. Right? So there's, in addition to the actual speech, what we record with the microphone, there's a series of intermediate actions that you take that produce a totally different, never before measured set of signals. So these include movement of the lungs, you have a beating heart as you're talking, you have vibration of the vocal folds that you felt, and then you have movement of the articulators. All of those have to work in a very specific way in unison in order to produce the acoustic speech signal. So we're all familiar with two-factor authentication. So think of another approach to recording audio that is akin to two-factor authentication. However, instead of having people do something specific, we measure both the acoustics, the words that are coming out of their mouth, the signal that's coming out of their mouth, but then also these physiological motions that are happening inside the body, these biomechanical motions, the movement of the lungs, the beating of the heart, the vibration of the vocal folds, and the movement of the articulators. So you have now physical authentication at the source of human speech. We spun out Origin Story from ASU last year, and the idea behind Origin Story is to develop a microphone that measures these two audio streams in parallel, authenticates that there's a real live human speaker producing the audio, and then embeds that authentication signal within the audio stream so that at the destination, like if you're on a Zoom call, for example, you can surface to the listener that, hey, you're talking to a real live person. And if these uniquely human physiological signals are not present, then you cannot authenticate as a human, and no verification is provided on the other end. Right? So now in this case, you establish this chain of trust from the words coming out of a live person's mouth to those words hitting a listener's ear on the other end. The sensor itself is based on radar, so it's a time-of-flight sensor. These are if you have a car, many modern cars now have radar sensors that detect motion on the side. This is a radar sensor that's specifically tuned to be able to measure the subtle biomechanical vibrations inside the body. Totally safe, very small. You can see there, It's on the order of a MEMS microphone in terms of physical size. And the idea is in the future instantiation of this, you have something like this inside a phone. So when you're recording, you record both the acoustic stream and the biomechanical stream, certify the media, and then send it over to the other side to authenticate. Just to give you a sense of why this works, so the top is an acoustic data stream where I've injected synthetic speech in red there. So the rest of it is my voice, with the exception of that red component. And in parallel, I've measured the physiological data stream. So you can clearly see the mismatch, right? Because those words didn't come out of my mouth, there is no corresponding physiological data stream, and so this would then fail the actual authentication. This is to give you a little bit of intuition behind how it works. And then the actual algorithms themselves, you can think of them as being split into two parts. So the microphone does two things in parallel. The first, it detects that there's a live human behind the microphone, and it does this using the physiological data stream. And so this, we measure the sort of unique to human physiological patterns, like a beating heart movement of the lips. But the output of this model is just, you can think of it as a liveness check, like similar to when you use FaceTime, when you use the video camera to open your phone. There's an internal liveness check to make sure that you don't have a 3D replica of my face. It's actually a live human, right? So that top data stream is sort of the audio equivalent of that. The bottom audio stream actually validates that the speech that you're measuring, that you're recording with the microphone, came from that physiological data stream. So it's a two-level authentication, and both need to pass in order for the speech to be verified as authentically human. And so what I've shown here is the performance of the models, the human presence model and the human speech model here using the confusion matrices. They both work quite well. And in fact, what you don't see here is the combination of the two, the performance of the combination of the two, because you see the AND operator there. You need to pass both streams before you can detect that this is a live human. So the false alarm rate is very, very, very low. However, there's about a 3 to 4% probability of misdetections when you combine these two data streams. Now, it's important to note the output of the actual microphone is a determination that whether a human is speaking or not. It doesn't say that this is Visar speaking. It says that this is a human speaking. However, it can be combined with things like voice biometrics. So imagine you have a speaker ID model where you enroll yourself into the model, and there's a voice footprint associated with your voice. Now, voice biometrics are common in many different applications, or they were common in banking applications before voice cloning came out and sort of made that not a viable approach to security and authentication. However, with the microphone now, you can think about stacking these claims on top of each other. So if you have the origin story microphone, the output is a human is speaking. If you combine it with voice biometrics, it's a human that sounds like Sam is speaking. So you actually get voice identification and to bring the identity component into this. Okay, so just to kind of conclude here, I think generative AI poses a problem to communication safety. Some of it is by virtue of bad actors having easy access to these models, but then some of it is just the uncertainty that's created with things like voice-based AI agents and being widely available, which I think we'll see in the not too distant future. As I've hopefully shown, I don't think that AI-based detection of generative voices is a viable long-term solution. And I think we're going to need hardware-based authentication. The thing that's interesting about the radar stream, why can we replicate voices and videos and images with such ease? The reason is because there's these large-scale data sets that are available on the internet. There is no incentive for anyone to give away physiological radar data. So I think there's sort of this additional layer of protection that makes this future-proof or robust to generative AI, in that data at a large scale for the radar data stream is not widely available. And as a result, by doing this physical authentication using a totally different modality, one for which this data isn't available at scale, this makes it the whole approach invariant to improvements in generative AI. In terms of the actual status of the technology, we've demonstrated this in a laboratory setting. We have a proof of concept to demonstrate that you can do this sort of validation. And we're now working to developing a situationally aware prototype of the technology and a minimum viable product in order to productize this. Somewhere along the way, I started out as an academic. I'm still an academic, but along the way, I became an accidental entrepreneur. So I think this is sort of one of the ways in which we're trying to have impact with the technology that's being developed in the lab, having real-world impact with it. And with that, I will stop, and I will take any questions that you may have. Yes?
So, yes?
So you say that this physiological stream would not be widely available and therefore robust towards generative AI, but in the end, wouldn't you have a lot of those data available if you normally then are sending both streams?
Yeah, so you're not sending both streams anywhere. So all of the processing is done on hardware locally.
Okay.
So, you know, this is whatever device I provide as a response to something that someone else does, someone can figure out how to hack. It's just a matter of the amount of effort required. In this particular case, it would take quite a bit of effort. You would have to effectively read the data from the hardware from lots of different devices in order to collect data at scale to be able to develop these models.
Okay, thank you.
Yeah.
And thank you for a nice talk.
Thank you.
Hi, thanks for the talk. I'm just curious as to how you encode the verification at the final signal as you're broadcasting it. So like, for instance, in a typical WAV file, you have like metadata,
Right.
and then you have the actual data block. So I'm just wondering, I mean, this is also, you know, with the potential of hacking the signal. I'm curious to that.
So there's lots of approaches to this. I'll talk about a couple. So there are some systems, like if you take Zoom communications, for example, there is a separate data channel that follows the actual audio, right? And so there you're not saving something as a file. This is a synchronous communication. So one approach would be to send this through the separate data channel. If you're talking about just the audio file, I think including it in the metadata would not be safe because anyone can go in and change the metadata. We've done watermarking. So in fact, in the example that I've showed with the physiological stream, you effectively encode a watermark, a time-varying watermark that can be read off the signal. Now, if someone tries to modify the media file in any way, the watermark fails, and so then the human authentication on the other end fails. And then a third approach, one that is relatively new, but I think it's gaining acceptance, is this idea of content provenance. So there's this C2PA standard where think of your metadata example, but think of that as existing on an encrypted layer on top of the file, so that if anyone tries to modify it, the whole file breaks. So you could easily integrate these sorts of verification signals within the metadata of an encrypted C2PA type system. Yeah, great question.
Do we have other questions? Any questions online? Not right now. So I'm curious because, as you said, you're an accidental entrepreneur. You're a researcher first and foremost, and here you're taking research and bringing it out into the world. Where are you on that journey with this particular project right now?
Yeah. So I would characterize this as being in sort of the early company building and idea building stage, and team building stage. So we're looking to recruit. So one of the things I made very clear, both to myself and then also in talking to potential investors, that I don't have an interest in leaving the university. So as a result, then we're finding the right team in order to take this idea and move it forward. And so we've identified some of the key players and are working to now move that from a concept, a proof of concept that exists at the lab, to an actual MVP. So it's still relatively early, but developing.
And do you have that team now at ASU, or are you looking for talent worldwide?
So we have a good part of the team at ASU, but we're always looking for talent and so it doesn't necessarily need to be at ASU. One of the benefits of being at ASU is that it's massive. So just like as an estimate, there's about 88,000 students at ASU's campus. And to support those students, we have a huge staff. So just in engineering, there's between 300 and 400 faculty that do research, and as a result, it's a wide talent pool and a diverse talent pool. So we've leaned into the researchers and advisors that exist within the ASU ecosystem, but we're very much open to others that want to contribute. I think one of the sort of the key next steps here, speaking from a sort of commercialization perspective, is identifying the right partnerships. Because this is a hardware solution, we have no intention of making a standalone microphone. We see this as an addition to existing technologies. Companies that work on headsets, companies that work on microphones, to include as an additional key component within their technologies for security purposes.
Perfect. New question coming up.
Thank you. So I have a background in rhetorics, and I really want to believe that human beings can recognize other human beings in language. But I know that that's being challenged now. But I'm just wondering, since we know a lot about mirror neurons today, so the way I'm feeling right now when speaking to you is affecting how you're feeling.
Exactly,
way,
yeah.
Right?
Yep.
And I'm just wondering, is there absolutely nothing going on the receiving end physiologically when we hear a human voice compared to an AI voice? Is there no difference?
So it's a good question. I don't think it's a question that's been answered. I think the one thing I'll say is, up until very recently, whenever you heard voice that sounded like human, there's nowhere else it could have come from, because they were the only entities that produce sounds in that way, right? That produce speech. And so by virtue of changing the input signal in ways that are imperceptible, I guess your question is, are there things where you maybe know subconsciously that this isn't a human, but that maybe consciously you're not aware? I haven't seen any work in that area. It sounds very interesting. Yeah.
Let's do some research.
Yeah.
It's regarding the two confusion matrices you showed. The top one for the physiological one. That performance, is that based on in-house synthetic data or real-life data? Because you talked about the data scarcity on that type. So is that something you collect a lot in your lab?
This is a good question. So here, these are based off of a study where we brought in 100 individuals into the lab, and we have them go through a series of conditions. One of the conditions is that they're speaking in the microphone. And there's a series of about 4 other spoofing conditions where we play synthetic audio through the microphone, and the person tries to somehow fool the microphone. So it tries to fool them by trying to mimic the synthetic audio, like moving their lips in unison with it. We play it through a loudspeaker and point the radar to the loudspeaker so that you have the vibration signal there. And this is based off of that data set.
Okay.
It's data from about 100 people.
Thank you.
We have one question online, and then I'm coming over to you.
Yes, so the question sounds like, I'm wondering if the ability to identify AI-generated voices varies within different languages, assuming AI is mostly trained in English sounds.
Yeah. I don't think there's any doubt. I think if you look at the performance of these models and the ability to detect real versus fake, it probably varies. Where it's more difficult with high volume languages like English, for example, or some of the Western languages where you have large training data. The flip side of that is that to actually build the detectors, you also need training data. So there's probably some interplay of how much data do you have to train a detector versus how much data was used to train the generative model. But I think in general, that's probably true, that if you have a high volume data language, then it's easier to, it's harder to detect real from fake. Yeah.
Hi. You mentioned some partnerships with external companies that produce external devices. I guess you don't have much power into what the quality of the voices are from mobile devices. Is the quality of these affect the just the final output of how much it does? And also, if you have to do some reducing the cutting the noise to get a better high quality of the voice, does that affect also the results? Or
yeah. Okay, this is a good question. So I'll take a couple of them in parallel. So the first one is that this probably wouldn't go into a phone as the first application. I think a more immediate application would be something like a headset, where you have, first of all, better control over the hardware, more degrees of freedom, and generally speaking, higher quality. That said, let's say eventually you get to the point where you want to integrate it into a phone. I think the MEMS microphones that are in phones are actually quite good, and you'd be capturing the signal right at the moment at which it's being emitted from someone's voice. When you say the audio quality is poor, I think you're maybe referring to once that is transferred or transmitted to the other end, where there's some loss that happens in the transmission process. Here, all of the processing is done prior to transmission, so there wouldn't be much of an impact in the downstream transmission process. I think that, that does bring up some unique challenges about how you hide the metadata or where you put this authentication signal in the context of something like cellular communications, and those are problems yet to be solved. But in terms of the quality, like data quality issue, I think that's a less of an issue in this particular application.
That's going to be all the questions we have time for today, but let's give Visar a big hand.
Thank you.